Class. So, welcome back from your weekend. I hope you had some time to relax. So, here we have a picture of a rock. It might not look too exciting to you, but for those of you who did your homework, you might have actually recognized this rock. So this is a very old rock, the oldest rock of Earth origin, they think. They think it's about 4 billion years old. So today we're going to learn a little bit more chemistry so that we can understand how they come up with these dates. So here's a tree. Again, if you did your homework, might look familiar because this is the oldest tree on Earth, they think. So the oldest living thing, like still alive on Earth. And scientists carefully found its age, and they think it's about 5,000 years old. Now, those are considered absolute dates, even though we don't know for sure, like 5,000, it is a numerical value. It might be 5,010, who knows? But 5,000 around, just like the rock was absolute dating with a numerical value. And the last one we're going to look at is the oldest piece of what they call the stardust. It was found in a meteor, right, that hit the Earth, and they dated it at 7 billion years old. So, to really understand how we date things, we do have to look at a little bit of chemistry. So, here's the periodic table that we talked about last week. I'm going to, on the next slide, so you can see this shows all the various elements. On the next slide, I'm going to not include this bottom row. These are called the rare earth elements, and we're not really going to be, they're kind of unusual, don't follow the chemistry rules. So we're not really going to be using them right now, although later on we might talk about uranium and plutonium, which you will find down here. But for today, so that I can make it a little bigger, I'm just going to enlarge it like that. So quick review, these are called elements. So hydrogen is an element, and that an element means a substance made of only one material. So only one type of atom, I'm sorry. So hydrogen as an element would be if you had, for example, a canister of hydrogen that had nothing but hydrogen gas in there. And so aluminum is an element you've probably heard of. So aluminum would element of aluminum is when only aluminum atoms are in there, and that's it. But most things occur as compounds. So, like here's carbon and here's oxygen. They combine together and form carbon dioxide, which you have in your sodas and you have in the air. But this is the periodic table of elements, and we're going to be talking about what these numbers mean on the periodic table. So, there's a little bit of review from Monday. So, this is the atomic, not review from Monday, review from last week. This is the atomic number of copper. So it has atomic number 29. What that stands for, if you remember, it has 29 protons. And then down here, we have the atomic mass number. The atomic mass number is 63.5. So that is an actual average mass, and that's what we're going to try to understand today. So how do you get this number, 63? It's the number of protons, 29, and they each weigh 1. Very easy to remember. The atomic mass of a proton is 1. And then remember, in the nucleus, you also have neutrons. So the atomic mass is the protons plus all the neutrons give you the mass. So let me show you some pictures. That'll help. So here's nitrogen. Atomic number is 7. So that means there are 7 protons in the nucleus. But the atomic mass number, the average, is 14.07. So this is the average atomic weight. And if we look over here, this one says it only has 7. So it is an average atom of nitrogen if I were to draw it. So 7 protons, remember they each weigh 1, and a neutron weighs 1. So 7 plus 7, we get our mass of 14. These little guys out here are the electrons. They are so small that they don't really affect the weight. It would kind of be like me getting on a scale and taking out one hair on my head and getting on the scale and saying, woohoo, I lost some weight. It is so tiny, it would not matter. So the electrons are important to the atom, but they do not affect the atom's weight or the atom's mass. So let's just look at a couple more examples. Here's hydrogen. So the 1, this is what it looks like on the periodic table. The 1 is the number of protons, but look at its mass here. Its average mass is 1, or average weight is 1.0078. So that's a really close to just 1. So what that would mean is that most hydrogens don't even have a neutron. All they are is 1 proton and 1 electron. So that is the atomic mass. But somewhere out there must be a hydrogen that's heavier than 1 because we have this average number. So that's the thing we're going to try to understand today is how we get this number down here. So here's a slightly larger atom, sodium. Sodium, this number's atomic number. It has 11 protons. And remember, they each weigh 1. And then the average of the sodiums weigh 22.99. Now, you can't ever have a 0.99 of a neutron. So when you're just drawing an average sodium, they're going to round up to the average number that most sodiums have. So this rounds to 23. Most sodiums would weigh 23. So what that means is each proton weighs 1, and you got 11 of those. So you must have 12 neutrons because 12 plus 11 is 23. So that's how you get that number. But it can be a little confusing, so I want to do a few examples. So first, let's just look at some terms. Atomic weight versus atomic mass. You notice I keep slipping back and forth, but atomic mass is the sum of the protons and neutrons of a single atom. So when I tell you to draw the atomic mass of this atom, you have to, that's where you would, like on the sodium, choose to do 12 neutrons because you're drawing a single atom. The atomic weight is the weighted average of all the isotopes of that natural element. So carbon here, the atomic weight is 12.0107. So we're going to find out why this is not a nice even number. And that's because there are things called isotopes. So an isotope are atoms of the same element, and they can have different numbers of neutrons. So the different possible versions of each element are called isotopes. Now, the thing to remember is they still have the exact same number of protons, but their number of neutrons change. If you were to change the number of protons, it's a completely different atom. So here we have 2 carbons, and it's written a little different. This will be our isotope symbol. So the atomic number is the same. They both have 6, but this carbon has a mass of 12, and this carbon has a mass of 14. Okay, so isotopes have different numbers of neutrons. So let's look at some hydrogen isotopes. So hydrogen only has 1 proton. The one we looked at, most hydrogens out there, almost all of them, because the average rate is 1.001, so they have a proton and electron. But there are some hydrogens out there that do have a neutron. So how much would this one weigh? What would the atomic mass of this particular atom be? It would be 2, okay, because proton plus neutron is 2. This hydrogen, it's still hydrogen because it has 1 proton. You may have heard of heavy water. That's when sometimes the water is made with hydrogens that are heavier. So it has 1 proton and 2 neutrons. So that means the mass of that particular atom is 3. But by and far, the most are just 1. But you do get an average, a weighted average on the periodic table. So I'll show you what we mean by weighted average. But let's do one more example. So this is a basset hound. If you've never heard of a basset hound, they're very cute dogs. I used to have one once. Very low to the ground, but very big still, big floppy ears. They all have certain characteristics in common. The average weight of a basset hound is about 58 pounds. Now, does that mean every single basset hound on earth weighs 58 pounds? Well, of course not. So you're going to have some variation. So this basset hound has the largest ears on earth. Oh, I forget his name. He has a name and he has the world record ears. So I figure this basset hound with his long ears, you know what? Those ears probably add an extra couple pounds. So he's still a basset hound. They still have everything in common: short legs, long bodies, big noses, big ears. His ears are just a little bigger. So he weighs 60 pounds. So in a way, these could be isotopes. Same breed, just a little bit different. And here we have, poor guy, here we have a basset hound who is too fat. Okay, these people need to walk him because what can happen to basset hounds? There's bellies can start to drag on the floor. It's so sad. So this guy is too fat. So he might even be above the average. The average is 45 to 60 pounds. So he might be above the average because he's so fat. So let's say this basset hound is so far above the average, he weighs 70 pounds. He's unstable. He's so fat. So these would all be isotopes, same dog, same characteristics, just like the protons give the atom its characteristic. These dogs all have long ears, they all have short legs, they all have long bodies. However, their weights are going to change a little bit, but while their weights change a little bit, they're never going to be, no matter how fat any of these basset hounds get or got, they're never going to weigh as much as a hippo. This is a completely and utterly different element to go with our example. Okay, so he is not going to weigh several hundred pounds someday if he keeps eating. So isotopes are kind of like the basset hounds, just they all have the same characteristics, but their masses can vary a little bit. Okay, so another example would be cars. So this is the Tesla. And if you look up here, these Teslas, like this one's the P85. I don't know what that means. It says it's a performance rear wheel drive. And then you've got other Teslas with different types of batteries, different amount of mileages. Probably some have leather seat. I don't know about Teslas, but things change inside the car. But the reality is, it's still a Tesla, just small modifications. So in a way, you could think of these as all isotopes of a Tesla. Okay, so I'm going to now switch to a simulation that we are going to you're going to do for your part of the assignment. Making these movies and making my PowerPoints is my part of the assignment. It kind of take a while, so now you get to do your part of the assignment. And so if you look at this picture, what this is trying to show you is the natural abundance of the two different types of hydrogen. The purple are the hydrogens that have a mass of 1. So all the purple dots, if you just took a random sample, would be the hydrogens with the mass of 1. But the hydrogen with the mass of 2 is green. It's right there. So that's the relative abundance of the hydrogen 1s compared to the hydrogens 2. So you don't see on the periodic table a mass of 1.5 because it's not that kind of average. It's a relative average. So all these 1s, there's so many more 1s, they get weighted more because there's rarely a hydrogen 2. So let's play with the app and then you'll do some work with the app. So I'm going to go out of my PowerPoint and go to the PhET simulation to show you how to use it. So there will be a link on Canvas for you to use this. So it's all about getting you familiar with the parts of the atom and what isotopes are. So here we just have hydrogen. It's stable. It's an isotope. If I add a neutron here, my hydrogen is now hydrogen 2 because see, it has a neutron, it weighs 2, and it's going to show you how abundant this isotope is in nature. It's not very abundant. 0.0115% of hydrogens are hydrogens 2. Let's try hydrogen 3. Uh-oh, it's unstable. So that's what happens to a nucleus if a lot of neutrons are in there, and we will actually be using that when we talk about dating. So notice it's unstable, and there is just a tiny trace of these in the natural world. Let's try adding a fourth one. And notice there are 0 known isotopes of hydrogen that actually have 4 of these. So you're going to be playing around with just some of these elements. Here's oxygen. It's showing you it has a mass number of 16, okay? Here is the average mass, the atomic mass and the mass number, okay? So the atomic mass, you can see most of them must be 16. But let's try something. Let's try to make it weigh 17. Notice there's 0.038 that weighs 17. Let's take the 7 out. Now it's 16. Let's see about 15. There are 0% of them that weigh 15. Okay, so this is how it works. You're just going to play around with this aspect. But the part I like the most is the mixtures. So if we click down here, we're going to see mixtures. And you can do two things. Here's nature's mix, showing you the relative abundance. So let's pick a different one since I already showed you hydrogen. Come on, internet. There we go. So this is lithium. So lithium 6, notice the atomic the atomic mass, the average mass on the periodic table is 6.94100. So here's how it looks in nature. Lithium 6 are the purple ones. So there's not as many lithium 6s. Lithium 7 are the green ones. So there's more lithium 7s. So here we have that relative abundance, okay? So 6.94 ends up being the average. Now you can make your own mix, which is going to be part of your assignment. So let me put these down. So if, for example, that in real life, half of the lithiums were 7 and half of them were 6, then you can see what the relative abundance of each one would be and what the average atomic mass is. If I add 2 more here, you can probably figure out what's my average atomic mass going to be, and you can see you're changing it. So you're going to play around with this in our assignment to see what it means. Now I've got 4 and 4, so my average atomic mass would be 6.5. But remember, the nature's mix actually looks like this. So you're going to get to play with all of these. Let's go to oxygen. So oxygen, you've got 3 isotopes. That's kind of fun. So you've got oxygens that weigh 16. And here's how you see 99.75% of them weigh 16. Only 0.038 of them weigh 17. See where I'm getting the numbers? And 0.205 weigh 18. So the 17 ones, the green one, here it is. There's hardly any compared to the purple. And the oxygen that weighs 0.205 are the red ones. So it's kind of fun to just go through and look at all the mixes. Let me show you fluorine though. Fluorine, look at that. There's nothing but one. There are no isotopes of fluorine. I am going to have an assignment for you to play around with this and hopefully get very comfortable with what an isotope is before we go on and learn how they are used in dating. Okay, thank you.